Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment&Health. Eco-Environment&Health is a journal initiated by prestigious scientists with a strong editorial board, including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design, and broadcasting. The experts will accompany you like an harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment&Health. Eco-Environment&Health is a journal initiated by prestigious scientists with a strong editorial board, including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design, and broadcasting. The experts will accompany you like an harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Hello, everyone. Can you hear me? Okay, thanks. So, first, let me have a short introduction. My name is Yanbin Zhao from Shanghai Jiaotong University. So, welcome everyone. Today, we have the opportunity to invite Dr. Gao Feng give us a EEH talk about his work, learning chemistry representation, environmental data science. First, let me have a short introduction about Dr. Gao Feng. Dr. Gao is currently a postdoc research scientist at Columbia University, Department of Environmental Health Science. We know this is one of the best departments on environmental science. Before that, Dr. Gao Feng received his PhD degree from Michigan State University and his bachelor degree in chemistry from Nanjing University. His research focused on environmental data science based on novel machine learning and deep learning methodology to incorporate with multi-omics data to study the fate and transport of environmental chemistries and their effects on human health. Dr. Gao has published nearly 20 papers in machine learning conference as well as in journals in environmental science, such as the best one, EST, EHP. So I think Dr. Gao has a very interesting background in chemistry, environmental science, and computer science. So now I give the time to Dr. Gao Feng. It's your time now.
Yeah, let me share my screen. Can you see my screen?
Yeah, no problem.
Yeah. Okay. Yeah, great. Okay. Yeah, it works. Okay. Yeah. So thank you for the introduction, and thanks for having me. Today I'm going to talk about our recent work on learning chemical representation in environmental data science. Yeah. So I'd like to start with a brief introduction to environmental data science. Environmental data science is a combination of data analysis and data processing methods with domain expertise in environmental science. This often includes novel computational methodologies such as machine learning and deep learning. With environmental data science, we aim to transforming raw, sometimes even unorganized data into understandable and actionable knowledge. In other words, with the help of novel mathematical tools, we want to discover patterns or knowledge that cannot be easily discovered before, or we want to reach the accuracy that cannot be easily achieved by previous models. My research focuses on environmental exposures and their impacts on human health. The question is, how can we incorporate environmental data science? How can we employ these cutting-edge techniques in helping us understand environmental exposures and their impacts? To study environmental exposures and their impacts on human health, one direction that cannot be neglected is the fate and transport of contaminants. The knowledge of the fate and transport of contaminants is important and necessary in assessing potential risks. Fate and transport of contaminants refer to the changes of contaminants. It could be chemically, physically, or biologically, and their movement through the environment. Information and models based on these exposure assessments can then inform public health and help us make cleanup decisions. So in today's talk, I will focus on the fate, transport, and toxicity of contaminants in the environmental data science. Indeed, there have already been hundreds of thousands of studies focused on the fate, transport, and toxicity of contaminants. Many of these studies conducted lab experiments to acquire valuable data on, for example, bioconcentration, dissipation, and many important properties of chemicals. And for toxicity, traditional in vivo experiments are usually conducted. So these experiments usually take a few weeks to several months. Sometimes it could even take years to finish. However, with the increasing number of chemicals, lab experiments can only test a small amount of them. Therefore, computational models have been used to assist this assessment. QSAM models, for example, the QSAM models, cognitive structure, activity, relationships could be used to build models and make predictions. However, these classic QSAM models are most linear. Most linear. So this is where the environmental data science comes in, where we can use novel machine learning and deep learning models to capture more complex nonlinear relationships. However, the performance of these machine learning and deep learning models heavily depends on the data representation or the features we are using, which is understandable because if you are feeding in noise into your model, you cannot expect anything useful comes out of the model. So since we are interested in the chemical exposures, their representation really matters. There have been a lot of studies on how to represent the molecules, and here I just list a few, like 3 of them, using molecular physical chemical properties or descriptors, or using molecular fingerprints, and using molecular graphs. Unfortunately, even if we have this representation of molecules, we still have one more issue here. Many machine learning algorithms cannot efficiently extract and organize the discriminative information from the data. Sometimes when we have too many features, we even have this so-called cursive dimensionality, which means the performance of model decreases as the number of features increases. And actually, this is quite common. For example, many linear models are often used together with some dimension reduction methods or filter selection methods. Therefore, researchers have used feature engineering, which relies on human ingenuity and prior knowledge to pick up some features for the model. But this is still labor intensive and requires extra steps in processing the data. What makes these things worse is that sometimes even the representation of the data itself cannot even be directly used by our models. For example, if we are using molecular graphs, it cannot be directly fed into a linear model or linear regression model or like a normal neural networks. Therefore, researchers have proposed this representation learning, which means learning representations of the data that makes it easier to extract useful information when building classifiers or other predictors. For example, if we want to here classify dogs versus cats, no matter how these cats look like, right? No matter what color it is, no matter if it's in the bed or on the floor, the representation with the cat should be similar to each other and should be different enough from dogs for this classifier to find this boundary and make the predictions. So classifying these cats and dogs look similar to human, but there are tough cases. For example, toxicity of molecules. So how can we find the boundaries here? How can we classify the toxicity of these chemicals? This is where the representation learning can help, and the learned representations of the molecules hopefully can reflect the patterns in toxicity. Indeed, many deep learning models have been developed to extract these more abstract and ultimately more useful representations. And once we have these learned representations, they can be used for various downstream tasks, for example, classification, regression, or clustering. Therefore, today, I'd like to share our work on learning chemical representations. I will start from a straightforward but effective example of linking molecular structures with bioconcentration of organic contaminants in plant roots, just to show how the selection of molecular descriptors can assist us understand the fate and the transport of contaminants. Then I will move on to our work in learning chemical representation from hundreds of molecular physical chemical properties for toxicity prediction. Finally, I will introduce a novel graph learning method we developed named geometry scanning transform, which can be used to learn graph representation in an unsupervised way. Okay, so the first part, linking molecular substructures with bioconcentration of organic contaminants in plant roots. The widespread of organic contaminants in agricultural soils and their transport from soils into plants pose potential threats to agricultural sustainability and eventually may harm human health through dietary consumption. An important characterization parameter to describe such accumulation of organic contaminants in plants is root concentration factor, RCF. Therefore, QSAR models such as linear regression models are used to predict the RCF. But these linear models cannot capture more complex relationships, so the performance varies from studies to studies. Besides, these models usually depend on molecular physical descriptors such as log QW or molecular weight or root lipid content. That's not able to directly link chemical structures with bioconcentration. In this study, since we are interested in linking chemical substructures with root concentration factor, so we utilize this molecular fingerprints, specifically the extended circular fingerprint. There are, of course, other fingerprints such as MAS, CCS keys, but we are especially interested in CFP since it can represent the presence of any substructures in the molecule. And it can be used as a feature vector of fixed length to represent the molecules so that we can fit it directly into the model. Also, by using the ECFP fingerprints, we can avoid the usage of specific physical chemical properties of chemicals. So the figure here gives a basic idea of how ECFP can be generated. So if we focus on the atom here, the oxygen atom here, and if we look at its surroundings, by taking just one step away from the oxygen atom, we can reach to two carbon atoms. And this is the substructure the CFP can find by taking one step from the center oxygen atom, and it will record this substructure into the fingerprint. And then by taking two steps away from the oxygen atom, we can capture a larger neighborhood. And these substructures can be encoded into the molecular fingerprint. And by using this molecular fingerprint, we can directly relate molecular substructures with bioconcentration of organic contaminants. Okay, so we collected a RCF data set that contains 340 data points covering 72 chemicals, and we also collect its related log QW, molecular weight, cell organic matter content, and root lipid content. And we propose using this gradient boosting regression tree model together with the ECFP to predict RCF. Gradient boosting regression tree is an ensemble learning method and build each tree step by step and minimizing the predictive loss. Okay, so we first show that ECFP can be used to distinguish the different molecular structures. We apply k-means clustering on top of the ECFP fingerprint of molecules and cluster these chemicals into three groups. So the first group here, which is the yellow dots here, consists of BDEs. And the group 3, which are the green dots here, consists of PAHs. And the group 2 is a mixture of chemicals and contain chlorinated and substituted aromatic or heterocyclic functional groups. As we show here, based on the ECFP, we can clearly see the structural differences among chemicals. They form different groups, which is important for our model since we are interested in using it to represent the molecules and related with our bioconcentration. We then conduct 5-fold cross-validation and compare the model performance of our model with other models, especially the QSAR model, the QSAR linear regression models here, just using physical chemical properties. Although I didn't show here, we also compare the performance with other machine learning models like random forest or neural network models. But eventually our GBRD CFP model achieved the best performance in terms of both R-square value as well as mean absolute error. Finally, we explored the relation between chemical substructures and the root concentration factor. We interpreted the model using two feature importance methods, permutation of feature importance and impurity feature importance. We were able to identify the top 5 most important substructures. Both methods actually identify the similar substructures. This includes functional groups containing oxygen and the chlorine and aromatic rings, and as well as this large pi systems, they are considered the most important substructures dominantly contributing to the prediction of log ICF. So this substructure actually also closely related to hydrophobicity and lipophilicity of chemicals, which is consistent with previous studies and show log QW is related to the log ICF. So this is a straightforward but effective example of showing how to link molecular substructures with bioconcentration of organic contaminants through choosing the appropriate descriptors. In conclusion, we show that the GBRT-CFP can improve RCF prediction compared to traditional linear models, and the GBRT-CFP can identify important molecular substructures related to root concentration factor. So in addition to the molecular fingerprints, chemical, physical, chemical properties are also widely used to represent the molecules. So in this part, I will talk about our work in learning chemical representation from chemical, physical, chemical properties for toxicity prediction. Evaluating the chemical ecotoxicity or the hazard concentration 50 is a valuable approach to identify potential hazardous effects of chemicals on ecosystems, and it is also of great interest in academic as well as in the regulatory communities. Toxicity testing has relied heavily on in vivo animal models, which is extremely costly, time-consuming, and low throughput. So researchers propose this in vitro chemical screening to efficiently identify hazardous compounds. However, it still requires labor-intensive laboratory procedures. Besides, the current in vitro method can't capture these complex effects such as endocrine effects and have limited ability to predict toxicity in vivo systems through the in vitro to in vivo extrapolation models. Therefore, in silico models have been proposed for toxicity prediction. In this study, we utilize a data set from US ETOX chemical database. We further collected physical chemical properties from previous literature. This includes hundreds of physical chemical properties, for example, 11 properties from the US ETOX itself, around almost 800 descriptors from USEP toxicity estimation software tool, and another 50 properties from QGProp, and together with the MOA class of the chemical. Finally, there is a total of 690 features and around 1,800 chemicals after removing uncertain and duplicate variables, as well as this not available values. Let me argue that with all these properties, with these hundreds of properties, many of them may be redundant, so a feature selection step may be needed, which is pretty reasonable. But instead, we like to develop an end-to-end deep learning model that can automatically learn the useful features without extra steps in feature selection. Therefore, what we propose is a supervised autoencoder model to learn low-dimensional representation of the chemicals and achieve dimensionality reduction. So this is a basic structure for an autoencoder. Autoencoder is an unsupervised deep learning model. It takes input features and learns the low-dimensional representation, or what we call the embeddings here in the middle, from the input features and through the encoder. Then the decoder will try to reconstruct the input features from the learned embeddings. Through this decoding process, the learned embeddings can contain the essential information from the input data. And by learning a low dimensional representation, autoencoder can work as a dimension reduction method. So what we do here, because we are trying to predict the chemical ecotoxicity or the H50 values. So we propose this supervised autoencoder model. So on top of the decoding process, we utilize the learning embeddings to predict the H50 at the same time. So that this autoencoder can learn more information, richer information related to predicting the HC50 values. Since our model has these two processes, the encoding, decoding process, as well as the prediction process. We also have two loss functions combined together as our loss function for our supervised autoencoder model. So the two losses are reconstruction loss, which measures the qualitative reconstruction of original features, and the predictive loss, or the prediction loss, which measures the quality of the prediction. So our model is trained together with these two losses. And to evaluate the performance of our model, we use three metrics here on the R-square value, mean absolute error, and root mean squared error. In summary, we input the 619 features into our autoencoder model, learn its low-dimensional representation through the encoding decoding process, as well as the prediction process, and finally predicts the HC50 values. Specifically, we reduce the dimension of 619 features into a dimension of 128. We actually have tested even lower dimensions, but the prediction accuracy just starts to drop. So we select 128 as our final reduced dimensions. We first showed that the learned chemical embeddings can reflect the patterns of HC50. So these are the learned chemical embeddings under their t-SNE coordinates. t-SNE is a visualization tool as well as a dimensionality reduction method, and can project the data into a 3D for visualization. So as we can see here, from left to right, the HC50 value change from larger ones to smaller ones, which demonstrates that our autoencoder model can learn effective low-dimensional representations that reflects the HC50 values. Since autoencoder can be seen as a dimension reduction method, we then compare the performance of our autoencoder with other dimensionality reduction methods towards predicting these HC50 values. This include PCA and UMAP. We compare the PCA when it reduces the dimension into 128 as well as 2256. Our autoencoder outperforms all the other models in all of the three metrics. That is the R-square value, mean absolute error, and root mean square error. Finally, we compare the performance of autoencoder with other machine learning models, such as random forest, polyconnected neural network, and rigid regression models. There are other models and then show here, such as Lasso, but we also compare our performance with those models, and our autoencoder achieve the best performance in terms of this R-square value, means MAE and IMMC. So in conclusion, the supervised autoencoder model we proposed provides a unique way of processing redundant high-dimensional input data that is different from other methods such as the PCA. The supervised autoencoder model can learn effective low-dimension representation related to HC50, and the learned chemical embeddings can be used to predict HC50 accurately. Now I have showed how we are using molecular physical chemical properties for toxicity prediction, and how we can use molecular fingerprints to link molecular structure with bioconcentration of organic contaminants in roots. So finally, I'd like to talk about a graph learning method we developed named geometric scaling transform. Since it can be used to work on molecular graphs. So the first question is, what is a graph? Graph consists of nodes and edges, where edges represent the relationship between nodes. For example, for a molecular graph, atoms are nodes, and the bonds connecting these nodes are considered edges. Actually, graph structured data are quite ubiquitous in our life. For example, social networks, right? Each individual can be represented by a node, and the relationship with other people can be considered as edges. And these graphs have even wider applications in recommendation systems when we are shopping, in recommending, for example, in recommending friends to you. It has been a really hot topic in recent years to study graphs and their representations. So in addition to the graph structure, there are also signals or features defined at each node. So these features are attributes of these nodes. For example, for a molecular graph, the features of this of the nodes or the features for each node for each node can be the atomic numbers or charges of that atom. Okay, so graph provides a unique way of representing molecular structures. However, the problem here is that normal neural networks or like fully connected neural networks or convolutional neural networks or like the simple like linear regression models, they cannot directly work on graphs because you can't just send a graph or like the JSON matrix of a graph to a neural network. Therefore, graph learning has been proposed. The graph learning method means that we develop machine learning models that works on graph. So it includes both supervised and unsupervised models. For example, graph convolutional neural network is one of the most popular graph learning methods. That's one of the supervised learning method. So the geometry scan transform I'm going to introduce today, it's an unsupervised graph learning method, which means you don't need to train your model to get the representation of these graphs. So geometry scan transform is constructed as a cascade of graph vivid transforms followed by nonlinearity operations. So I must start from talking about how we build a random walk, graph random walk, and then move on to how to build a graph vivid. Then the details the geometry scaling transform. So given a graph G here, we know it's the JSON matrix A, which reflects the connectivity of the nodes and the corresponding degree matrix D. We can design a random walk P here, as shown here. So random walk shows the probability of moving from one node to the other node in one step. With that random walk, we can now define the graph wavelet, which is defined as the difference between linear random walks at different time scales, which is psi J here. And then we can have this graph wavelet transform. And the left part, the P part, is considered as the low pass filter, which can average the signals on the graph. And the psi J here is the wavelet or the high frequency filter here, which can extract high frequency information from the data. So here we realize the wavelet transform by applying the graph wavelet on directs centered at two different locations. So we can see here with the increasing of G, we can extract features of the graph at multiple scales, which results in a multi-resolution representation of graphs. For example, if we look at the bunny here, for the node centered at the bunny's ear, by increasing G, which is the scale of the wavelet, it will diffuse to the whole body of the bunny and extracting from local to global features of this graph. And similar here in the Minnesota road network graph, also starting from a node, and it will diffuse to the whole graph and extracting these features. And this is how the graph wavelet transform looks like when you actually apply it on the graph. Now that we have built this graph wavelet, we can move on to the geometry scaling transform. So our geometry transform is constructed in a multi-layer or like a multi-order fashion. So the first order features is calculated through the summation operator of the original features or the raw features. So the summation here itself works as a low pass filter, which basically averages the signals on the graph. This summation is necessary because it can help us achieve permutation invariance. But by doing this summation, we are actually averaging the signals of the graph, and all this high frequency information is missed. Therefore, to recover this high frequency information from the graph, we apply our graph wavelet, like in the first order features. We will apply our graph wavelet to recover higher frequency information. and then we do summation to achieve the permutation environments again. And then we can further recover more high-frequency information by providing the graph wavelet in the second order again on top of the first order features, and then extract more features. And by calculating all the three orders of features and combining all these features, we can obtain our final graph representations. So this shows a general flow of applying geometry scaling transform for graph data analysis. So with the input graph, we can generate its corresponding adjacent matrix and obtain the associated node features, or the signal vectors here, the F here. We can then build the diffusion wavelets based on the graph random walk and apply geometry scaling transform on top of the signal features, signal vectors, to extract graph representations, or what we call the scattering coefficients. And with this graph representation, we can use it for various downstream tasks, such as regression, classification, or clustering. And it can be used with any traditional Euclidean algorithms like supporting vector machine or principal component analysis. So the first task we did is the comparison of various models on graph classification. Here is a summary of the data sets we are using for comparison. And these are pretty standard data sets that people are using for comparing the performance of graph learning methods. So here, the NCI1 and NCI109 data sets predicts whether chemicals are assessed as positive or negative to cell lung cancers. We also have other data sets like the DNDN proteins, which is just predicting whether a protein is an enzyme. And we also have the PTC data set here, which predicting whether chemical compounds are carcinogenic in rats. So all these data sets, so they include both binary classification and multi-class classification. And these chemicals and the proteins can also be represented as a graph. So combining our geometry scaling transform with a supporting vector machine, which means we use our geometry scaling transform to learn the representation and feed it into a supporting vector machine classifier. We compare the performance of our model with 15 leading machine learning and deep learning models. Our results show that our geometry scaling transform supporting vector machine classifier reached near state-of-art accuracy. However, I'd like to note here, the method we are comparing here are all supervised models that require training, while ours are just based on unsupervised models, which we don't need to train, but directly extract these features by using these graph wavelets. So this comparative result indicates that our geometry scaling transform can effectively learn graph representation without training. So one more thing here, and I'd like to show is the ability of using geometry scaling transform for dimensionality reduction. So the Euclidean notation of graph, the Euclidean notation dimensionality for graph is not naturally available. But for this enzyme data set, which on average has 124 edges, almost 30 vertices, and 3 features per vertex per graph, we can consider it as a very high dimensional data. And here we now show that a geometry scaling transform can enable significant dimension reduction and still can remain relatively good model performance. Indeed, with the decrease of dimensions here from 44 to 9, and the exponent variance dropped from 100% to 80%. It only causes a very small impact on classification accuracy. The classification accuracy actually just dropped to like 3 or 5%. So we show that the geometry scaling can enable this significant dimensionality reduction. We actually have multiple results by applying the geometry scaling transform on social networks. And we also test its performance and low training data availability. But I'm going to skip this because this is basically more social networks. So I'm going to skip that for today. So in summary, our geometric scaling transform is constructed as a cascade of graph-weighted transforms followed by nonlinearity operations. And these scattering features can serve as a universal representation of graphs. Most importantly, the geometric scaling transform provides a new way of computing and considering global graph representations, and is independent of specific learning tasks. This is especially useful, especially considering many environmental data does not have lots of data points. So for this data set containing chemicals, using geometric scaling transform can learn useful representation and then use it for various downstream tasks. Okay, so finally, I just want to come back to this slide. And so the 3 projects today I talked about is just one small portion of what the environmental data science can do in understanding the feed, transport, and toxicity of contaminants. By employing these novel machine learning and deep learning techniques, there are more and more studies on linking these environmental exposures and environmental health in terms of building predictive models and discovering novel biomarkers. Hopefully, this can facilitate our understanding between human and the environment. Finally, I'd like to thank all the collaborators. First of all, Dr. Bagrali, who is my advisor at Columbia, and Dr. Shen, who collaborated with me on many of these projects, and Dr. Hen, who worked with me on the geometry scaling transform when he was doing, he was a professor at Michigan State. And I also thank Dr. Zhang and Dr. Li, who are from Michigan State University, worked with me on a lot of these projects. And there are so many fundings we'd like to thank. And we also want to thank the HPC resources from Michigan State University, which provides high performance computing services. And yeah, so that's my talk today, and happy to take any questions.
Okay, thanks, Dr. Gang, for your interesting talk. Personally, I'm very interested in your work and maybe have some questions. But firstly, let's have some questions from our listeners. So, any questions? So everyone, if you have questions, can ask directly or leave questions in our Zoom, chat room, okay? Mm-hmm.
See, Dr. Zhang has a question.
Well, yeah, Dr. Zhang.
All right, thanks, Feng, and it's a great talk. And I have rather a general comments, like where do you see in the next 5 to 10 years in terms of the like the development of the field in term for data science or machine learning or deep learning in the environmental science and engineering? So do you think our students are prepared for this transformation or evolution? Like, if we are not, what would be the next step for us to do?
Yeah, I think actually there are a lot of departments or universities they are realizing this issue, the transforming from pure lab experiments to the analysis of the data using novel mathematical tools. And so I have seen a lot of departments are opening this all kinds of environmental data science program. I think Michigan State also has this computational science. Some professors there are focused on environmental science. So yeah, I think it's always good for students to get trained partially, even partially in this basic mathematical courses or like machine learning courses. So will be helpful not only in analyzing this environment data, but also in terms of like career development, and in terms of like the development of environmental data science. I think like in the future there will be, of course, more and more advanced, but as well as more easy to understand machine learning and deep learning models for to be applied in the area, so that we can not only discover new knowledge, achieve better prediction performance, but we can also enhance our understanding of between environment and human.
Thank you.
Okay, any more questions? So Dr. Gao, I have a simple questions, and I'm not an expert on computer science, so much more from an expert. So basic questions, in the second topic you talk, and you said you got about nearly 700 features for chemicals, for each chemicals for the model development. So I'm not sure where these features come from. Is there some database or you generated from in some way? Can you give us a short talk?
Yeah. So so the chemicals, the chemicals are from the USC Tox database, and these physical chemical features are collected from literature. There's the paper, they calculated all these physical chemical properties, and actually many of them are from like commercial softwares. Yeah, so but it's so we can say like we need to if we want to calculate all these so many properties, we will have to like sometimes we need to pay for some softwares. So that's why one of the reasons a lot of people are interested in using like fingerprints or like molecular graphs to replace these molecules to avoid the direct usage of molecular physical chemical properties.
Okay, thanks. So this means know enough free databases for this information, right?
There are some free softwares that can help you to calculate physical these properties. But I guess to compute so many, there is some paid service.
Okay, thanks. We still have time for a few questions. So anyone? Let me see.
So I have another question. Like, if you want to give a students a suggestion on how to move towards this kind of a study, like what should they do? Like, if I'm a student in the environment science engineering, and I was trained in probably biology, ecology, or chemistry, or physics, or sometimes engineering. So I don't get trained on like computer sciences, or I don't have a good training in mathematics, but I'm quite interested in machine learning, deep learning, and in data science. And what should I do?
Yeah, I guess online courses it's good way to learn this new information or some basic knowledge. And I'm thinking like there are also like build collaboration with professors from other departments, from this computational department or computer science department. Myself has a background in chemistry and then in environmental science. But during my PhD, I looked for the collaboration with a professor from the computational science department, and we worked together on some projects. And and it turns out well. So yeah, so I guess being so I think I encourage students to look out for help from other departments and to assist the study.
Thank you. Yeah, I think the suggestion would be very much appreciated by our students. Thanks.
Sure. Yeah. I guess if students ask for help, even they're from professors from other departments, they will be helpful and they'll be willing to provide their perspectives and in design projects and in all kinds of things related to machine learning or in the field of computational science.
Dr. Gao, I have another question from the listeners. So let me see. Is there a way to make a model based on 3D structures of chemical molecular? Is there a way to?
So it's combining these three.
I think this means based on the 3-dimensional structure of chemicals, can we make a model, a toxic model, to predict some its toxicities?
Okay, so utilizing all three this representation of the molecules, right, and make a prediction to predict the toxicity of the chemicals. Oh yeah, I guess yeah, I guess sure. I mean, because you can have 3 different models, each you feed your different descriptors like molecular fingerprints and molecular graph into different models, and then you input it into, and then you connect all these learned representations with for example, some neural networks, and then make the predictions. I think it's definitely possible, and but I haven't seen people done that before, but I think it's definitely possible. Just make a very huge model, which each module process one kind of descriptor, and then you can combine them together and make the predictions.
Okay, I think this is more difficult, right? And so
yeah, I mean, it's a combination of 3, how you want to build your model, right? It will be a combination of 3 different models, and then you connect them, you combine these features. Yeah,
I think we tried previously on this work, but maybe it's too difficult for us. And do you know if anyone or any group has such kind of work?
Oh, you mean combining these descriptors?
Yeah.
I'm not sure, but I can say that the advantage here, the benefits here, you can actually make it like an assembly model, right? Sometimes the physical chemical properties can work better. Sometimes the fingerprint work better, or sometimes the molecular graph work better. So combining these 3 and with appropriate modification, I guess, yeah, I mean, it could be a good model.
Okay, here is a new question. How to evaluate the accuracy of this machine learning method with others? Are there any drawbacks or constraints in applying this method?
Okay, yeah. So to evaluate the accuracy of the machine learning model, we usually choose, especially when we want to compare to other models, we usually consider the same cross-validation method. For example, if other models are using five-fold cross-validation, we will also use five-fold cross-validation, and we will choose the same metric. For example, if the other models are using root mean square error or R-square values or AULC, so we just choose the same evaluation metric. So we just want to make sure the method is the same across different models, so that when we are reporting it, it contains less bias. constraints in applying the method. Yeah, one of the concerns I can see here is that sometimes the other models don't report all of these values, right? Some models, they may only report the R-square value. Some may only report the mean absolute error value. So in that case, we usually rerun their models and follow the exact steps as they described in their model, and repeat the experiments and report the missing values there. Yeah, hope this answers the question.
Okay, so I could see a new question from the chat room. So why did you choose to use ECFP instead of circular fingerprints on others?
Oh, yeah. So so the ECFP actually stands for the extended circular fingerprint. So it's actually that's the circular. But maybe I'm thinking about like other circular fingerprints. Yeah. So one reason we're using ECFP is because we want to represent it as to relate the molecular substructures with the bioconcentration factor. So there are of course other fingerprints like MACCSKs, right? So each value there represents whether or not a certain molecular substructure exists, but it cannot capture all the molecular substructures. The ECFP can achieve that. So we decided to use ECFP over other fingerprints to link out to link molecular substructures with root concentration factor.
Okay, do we have any more questions? Okay, I think if we have any more questions, maybe we can ask Dr. Zhang, do you have any more questions?
No,
Okay.
I just want to thank Dr. Zhao for hosting this presentation, and thank Feng for giving a great talk. Thank you.
Okay.
Thank you.
Thank you, everyone. So if we have any more questions, maybe we can ask after this talk, this meeting. And at the last, I want to thank Dr. Gao for this interesting talk, and also for EEH for this very good, very nice organization. And at last, thank you everyone for listening. So I think it's time to end. Okay.
Thank you for having me.
Okay. Bye bye, everyone.
Bye.
Bye.